All right. So, last lecture, let's recall what we did. In the last lecture, we were at the point where we were looking at the concept of a hole, and what we said was that if you have a valence band which is full of electrons, except for, let's say, one missing electron here, which has gone over to the conduction band, then the current carried by all the electrons in this valence band can be modeled in terms of current carried by that missing electron here, that missing state, if we assign a positive charge to it. Okay, so instead of talking about current carried by huge number of electrons in the valence band, we can alternatively talk about current carried by this particular hole here. Okay, so that was the concept of a hole which came out from the band theory here. And as I said, from henceforth we will not talk about we will not think of hole as a vacant state and all that and keep on talking about it. We'll treat it as if it's a real particle with a positive charge with a certain mass. Okay, all right. The other thing is, if you look at the energy band diagram, if you have an electron here, let's say I put it here, obviously the electron would try to go to the lower energy state and the electron would move here. All right, the electron would start from a higher energy and move to lower energy. So whenever we draw this EK diagram and other energy diagrams that you will see, the energy E refers to energy of an electron, right? So in that case, keep in mind what would happen to a hole. Let's say if I put a hole over here, right, at some energy E. Now this energy E refers to energy of an electron, does not refer to energy of a hole. So we know that energy of an electron increases as you go up here. And therefore we found the electron came down from higher energy to lower energy. What happens to a hole? The hole, on the other hand, if you put it at an energy here, this for a hole is a higher energy as compared to this particular energy. The hole would actually move up in energy. Okay. Now, just as I said, forget about the concept of a hole as a vacant state. We'll do that after half a minute. You can see here why the hole is moving up, right? You have a vacant state here, right? And you have all these electrons at higher energy. So electrons would obviously fall into that particular vacant state here, right? And that vacant state here moves up to that particular value here. So keep in mind that whenever we draw energy diagrams, the energy refers to electron energy. And in that case, the electrons try to move to lower energy. The hole tries to move to higher energy here. Okay, the hole tries to move up. All right. Anything wrong with this EK diagram? Can you spot the error? What is the error in this EK diagram? We said EK diagram has to be symmetric. Whatever happens for a positive K, same thing must happen for a negative K. There's a symmetry in a crystal. There's symmetry in a lattice, right? So I can't have an EK diagram like this here. Okay, so this is wrong here. It violates that symmetry here. All right. The other thing is, so I have an EK diagram that you see here. We said each one of them represents a band. And the next claim that I'm going to make is the following. The electrons, let's say I have some electrons in the conduction band. The electrons will stay close to the bottom of the conduction band. Most of the time they will be here. Now why am I saying that? Well, let's look at, I have this energy band here. And how many states are there per unit volume? As I said, each atom contributes like one state. So the number of states that are there, number of energy states available here is of the order of number of atoms per unit volume. The order is 10 to the power 22. A typical electron concentration would be how much in a semiconductor? Of course, it varies a lot. A typical you can take as a number as 10 to the power 17. Right? What does this tell us? What fraction of the states that you see here in the conduction band are occupied? 10 to the power 17 divided by 10 to the power 22. So very, very tiny fraction is occupied of the band, which means what? The electrons are all at the bottom of the conduction band here because they would all prefer the lowest energy state here. So and the rest of the band that you see here is all empty here. All empty here, all empty here. So they're all occupying the bottom of the conduction band. Okay. So that's the first point. The second point is, you may wonder, okay, this is at equilibrium. Suppose I apply a field, and we know that the field F acts upon the K momentum, and can't my electron then go to higher energy part here or not? Okay, so let me show it to you that even under field, the electron will not go very far from the bottom. Okay, how do I show it? F equal to h bar dk by dt. So we had this equation, force is equal to basically second law, dp by dt, p momentum is h bar k. All right, let's calculate how much will be the change in k as a result of force applied in a certain time interval delta t. Now we know what happens once the electron, I had mentioned to you that once an electron gains energy, what happens to electron frequently? It gets scattered. And what is the typical scattering time? Let's say tau, and the scattering time is like 0.1 picosecond. Right? So what will happen is when you apply a force, the electron will of course gain energy from the force applied, but then very soon what happens? It gets scattered. It loses that momentum. Right? So what is the change in dk that happens is equal to F by h bar times roughly the scattering time. That's the amount of time that the electron gets to gain energy from the field, and after that it gets scattered and it loses. Right? So let's calculate what is delta k here. Now also, what I will do is I will take delta k and normalize it by this total length here, which is pi by a naught. Okay? So delta k by pi by a naught is equal to then this particular term here. And let me put in some typical values here. Typical values, let me take lattice constant A naught as 5 angstrom, electric field as 10 to the power 5 volts per meter, which is like 1 kilovolt per centimeter, a moderate amount of field. Tau, as I said, scattering time is 0.1 picosecond. And then this delta k by pi by A naught turns out to be 10 power minus 3. What does it tell? That even when I apply a field, how much change in delta k will I cause? It's a very small fraction of this pi by A naught that you see here. Which means what? That even when I apply a field, my electron is not going to go very far from the bottom. It's not going to go very far, and therefore my electron is confined. The claim that I'm making is electron under typical cases is confined to the bottom of the conduction band. Same thing that I just said, I could say it for the holes as well. The holes are confined to the top of the valence band here. Okay, so all my electrons are here most of the time, and most of my holes are at the bottom of, at the top of the valence band here. Okay, all right. So similarly, holes stay close to the top of the valence band here. Then this brings out interesting thing that if my electron is always at the bottom of the conduction band, and at the bottom, note that it's a minima, and we said that we can model the EK diagram as some quadratic here, because we can do a Taylor series expansion. The first derivative is 0, this being a minima, and therefore E minus EC can be written as CK square here. And therefore what it is telling us is that we can model our electron in terms of an effective mass. Okay, if my electron were going very far in my EK diagram, then I couldn't have done this. But that's why I sort of showed it to you that under typical cases, electron is at the bottom. Even when you apply a field, it stays very close to the bottom here, which means that my electron can be approximated by this kind of an EK relationship as a quadratic relationship. And then a simple comparison of this EK relationship with h bar k square by 2m tells us that my electron can be modeled in terms of an effective mass. Okay. All right. And therefore, the effective mass is a very important concept, and one can then consider an electron. One can forget about, in some sense, about the EK relationship and all that, and one can think of electron as free, but with moving within effective mass here. And as an example of effective masses that you see here, these can be measured as well. Effective mass in silicon for electrons, effective mass in silicon for holes, for silicon here, germanium here, gallium arsenide, and indium arsenide. And these values are well known for a host of semiconductors here. One point to remember is all these things that we are doing, effective mass and all that, these are all models. And a very general statement is a model is always a sort of an approximation for a particular purpose. And these masses that we have written here, these masses, I won't go into the details. These masses are appropriate if I'm looking at conductivity, if I'm looking at motion. If I'm looking at something else, I may approximate it in a different way, and I will get a different effective mass. Okay? So effective masses are nothing but models, and models are valid depending on what your purpose is. Okay? So these are conductivity effective mass, and the values are given over here. Okay? Note in most cases you will find here that the holes are heavier as compared to the electrons here in all of these cases here. All right. Then there is I've been showing EK diagrams like this here, where you find that the electrons exist here, the minimum of the conduction band is here, the maxima of the valence band is over here, and minima and maxima exist at the same K value. And such a semiconductor, we call it as a direct semiconductor here. One can imagine where the minima and the maxima occur at the same K value. One can imagine a semiconductor like this here. So a hypothetical case here, where you can see here the minima of the conduction band is here, and the maxima of the valence band is here. So where would my electron prefer to be? Always at the minima. It would prefer to be here, and the hole will prefer to be here. So now the electron under normal circumstances is at this K value, and a hole is at this particular K value. Such a semiconductor that you can see here is called an indirect semiconductor here, where the minima of the conduction band and the maxima of the valence band, they are not at the same K value, not at the same wave vector value here. Now you can imagine a little bit of trouble here, right? Trouble in the sense, as I said, the electrons are going to stay here, and the holes are going to stay here, right? At the bottom of the conduction band, at the top of the valence band. We said when you apply a field, what does a field do? Field doesn't change K by much here, right? Field cannot change K by a lot here. So electron is going to stay here, somewhere in this valley here. The hole is also going to stay somewhere here. Then how did I take an electron? How did I create a hole? How did I take an electron from here to here? How did that happen? Who caused that change in K? How did I get this large change in K? So remember, eventually the electron, initially the electron was here, and then I promoted it to over here. How did that change in K occur? The field cannot do it. What caused that change? Huh? Okay. So how did it happen? Well, for that to understand, we have to note that we are talking about a ideal semiconductor here with no imperfections. Normal semiconductor, what would happen is there would be defects there. Not only that, there are vibrations in the lattice here. The vibrations that are there in quantum mechanics, the vibrations in a lattice are modeled in terms of another quasi-particle. Just like, electromagnetic wave is modeled as a photon, the vibrations in the lattice is modeled as a quasi-particle called phonon. And the phonons carry, note that K is nothing but, H bar K is nothing but momentum. Phonons carry a lot of momentum. So electrons can interact with the phonons, and together then they can make a jump here. So phonons would supply the change in momentum that you see here. And so this whole process is anyway thermal, if you realize. Thermal energy is what is taking an electron from here and promoting it here. And thermal energy or vibrations, they can be modeled in terms of, we'll talk a little bit about it later on. It can be modeled as phonons, as quasi-particles, which have a lot of momentum in them. Okay, and they can help you in translating this particular part here. So as you absorb a phonon, you can not only get a change in energy, but you can get a change in momentum also. The other thing is, all right, so the other thing is that, yes, we've been talking about a lattice like this with a band and with a propagating wave function, right? And we also said that suppose that in my lattice there is a defect. What kind of a defect? Well, maybe there's a vacancy, right? There's a vacancy, or maybe I've introduced some impurity atom. What these defects often do is they introduce localized states. Now remember, these states, why did they become a delocalized state? Because of the symmetry that you see here. I have a large number of wells here and they interact, and because of the symmetry, they become delocalized over the entire lattice here. But I have one single defect here, and then very far away, I have another defect here. So the defects will not introduce delocalized states. Defects would introduce only localized states here. Localized states, which means a defect would be, its wave function would be localized in a very small spatial domain here, right? Unlike a delocalized state that you see here. All right, so defects would be highly localized in space, okay, because they're very few in number and they're random in nature, and therefore you don't get a delocalization that you see. So now if you see the defect is localized in space, how do I represent this kind of a defect? Suppose there's a defect here in my lattice, And they're very few. So by and large, I can think of my lattice as the same band and everything else. The defect acts as a small perturbation. How do I look upon my defect? Well, if you think about it, if you look at this defect here, whose wave function is localized in a very small spatial domain, you know that this wave function, I can model it as ak exponent ikx here. If you recall your Fourier analysis, what does Fourier analysis tell you? You know, if you have a, let's say, cosine in frequency domain shows up as a one single frequency, right? Like as a delta function. But if you have a function which is localized in time domain, how does it show up in a frequency domain? It just spreads up, right? The frequency domain is like all frequencies are present if you localize it in the time domain. Same thing is happening here. You see, I have a function which is localized in the spatial domain, and in the k domain, what happens is it just spreads out. Okay, something which is completely delocalized in the spatial domain, how does it show up in the frequency domain? A very single value of k. Remember, this cosine e to the power ikx is like one uniform k. So one precise value of k, but completely delocalized in the spatial domain. Now here is something which is localized in the spatial domain, and what will happen to it in the k domain? It will get totally spread out in the k domain here. So if I have a localized state, how do I represent it in the energy Ek diagram here? All right. So this is how I represent. So this is my conduction band and valence band here. My localized state, which was some energy E, in the Ek diagram, it appears like this here. It has a very sharp energy, precisely defined energy. Its k value is not defined. I mean, it's just spread out. Okay, so how does it look like in the Ek diagram here? It looks like this dotted line that you see. A defect inside my lattice. Looks like this single level here. So now you can see how the defect also helps in moving an electron from here to here or moving an electron from here to here. Because a defect has it allows large values of k here. So what can happen is the following. You can imagine an electron being captured by the defect here, right? The defect is interacting with this electron here. Note that defect has the same k here. So defect interacts with the electron here and then moves the electron back to here. So defect provides a mechanism of moving an electron from this state to this particular state and back and forth here. Okay, so defect plays that particular role. The phonons, as I said, lattice vibrations play that particular role of moving an electron from a different value of k to a different value of k over here. Okay, so phonons and defects play an important role in moving that here. Okay, so that's an indirect semiconductor where the bottom of the conduction band differs from the top of the valence band here. Now, the trouble that comes is some of the places where this distinction becomes important is in light emission. If I have in this particular case here, if I go back and look at a direct semiconductor, let's say I have an electron and I have a hole, right? Now, note that my electron is now coming down into the hole here. And what does it do? The energy it releases in the form of a photon. Now, photon, you can very easily calculate. Photon carries very little momentum. Photon carries very little momentum. And therefore, as you go from here to here, because the photon carries very little momentum, therefore, this is fine, right? You don't require a change in k value here. K is what represents momentum. So as you go from here to here, it doesn't require any change in momentum. And therefore, my electron can go from here to here and emit light. On the other hand, for an electron to go from here to here and emit light becomes difficult because a photon doesn't carry momentum. Now, in addition to that, what do you need? You need a phonon. And then it becomes less probable. And so typically in these cases, in an indirect semiconductor, what happens is when you get an electron in a hole, typically as I showed here, the defect will capture it. All lattices will have defects, so the defect will capture it, and then the defect will bring it back to the hole, to this one. And you don't get any light emission in an indirect semiconductor like this. Okay. While in a direct semiconductor, the defect in a direct semiconductor also, if I have an electron here, the electron can be captured by the defect, and then the defect can bring it back to the valence band. That also happens. But the other process is also there, that I can directly go from the conduction band to the valence band and emit a photon here. So this distinction between direct and indirect becomes important when I start looking at light emission. Most of the semiconductors which are good emitters of light, they are all direct semiconductors. They are not indirect here. Silicon for us is an indirect. Okay. So let me show you EK relationship for a silicon here. All right. So it's more complicated. Now silicon, of course, so far I've been showing you EK relationship for one dimension, right? Only one dimensional lattice, and the only direction was kx, right? Silicon, of course, is three dimensional, and then you talk about different directions here. This is 1, 0, 0 direction, and 1, 0, 0, and this is 1, 1, 1 direction here. Half refers to 1, 1, 1 direction here. So different directions, and you can see here there are different bands here. This band here, several. So it's a complicated EK diagram here. There are many branches of EK diagram that you see here. All this that you see here, this part is where the valence band is. This part here. And this part is all at the top that you see here is the conduction band here. So typically, my electron in a silicon, this is the bottom of the conduction band here. And typically a hole would be here. And so silicon is an indirect semiconductor here. Okay. Another thing that you see here, right at zero, I have two EK branches here. One branch that you see here, this one, and I have another branch which is going like this here. Two branches are there of EK diagram, right? If I look at this first one, which goes like this, effective mass for this one compared to effective mass of this one would be? Whose effective mass would be larger? This one would be higher effective mass, while this one would be lower effective mass here. So when I have a hole here, the hole can exist in both this one here as well as this one here, because both of them are sort of degenerate at this particular point here. And therefore, what we have is a concept in silicon and other semiconductors of two kinds of bands present here. One is what we call as a heavy hole band, heavy hole here, right? This branch here. And the other one is what we call as a light hole. And you can see the effective mass for a light hole is 0.16 m naught. The effective mass for a heavy hole is 0.49 m naught here. So right at this particular point here, both of them have the same energy. So when you create holes in your semiconductor, the holes will go in both light hole band and as well as a heavy hole band here, because both of them are degenerate here. Okay, at this particular point here. All right, so I just wanted to, we will not bother about this, but just wanted to introduce to you the fact that EK diagrams are, for a real semiconductor, are far more complex here. Many branches are there that you see here. And in the valence band, you find two of them are, meeting at the same place here. And therefore, you have to consider both the branches, heavy hole and light hole here. Okay. Conduction band, of course, there's nothing of that sort here. There's a well-defined point here. They're not 2, 3 here.
How is the diagram obtained?
How is the diagram obtained? Well, you can do the calculations. You can do the calculations. You can do some measurements also, which can indicate the different parts that are there here. Okay. For example, you can see absorption experiments can tell me if I do absorb in silicon, for example, this is 3.4 eV. If I do give a photon, it's possible to go absorption and have a 3.4 eV. So absorption experiments can show you the features of an EK diagram, and many of these are calculated. So all right. Yes. No. Okay. The diagram is now drawn for different directions. The same diagram is showing you for two different directions. One is for 1, 0, 0, and the other is for 1, 1, 1. So remember, 1, 0, 0 positive, 1, 0, 0 negative are the same, right? So it's not drawn so this is only one direction and this is the other direction. Okay, so in two different directions, I have different EK diagram. But in the same direction, whether positive K or negative K, I'll have the symmetry. Okay, so don't get confused by this one here. It's just that in the same diagram, you want to show as much as possible, so you can show two diagrams, two directions here, right? Yeah. All right, so that's the EK relationship. So the picture then that we have is the following then, that even though I have an EK relationship like this here, my electrons are at the bottom of the conduction band here. And this is the energy versus momentum diagram here. I can also draw energy versus space position. And in that case, the two edges of the band are EC1 and EC2. So I denote EC1 and EC2. And remember, all my electrons would be at the bottom of this conduction band here. Similarly, the valence band I can draw as between this point and EV1 and EV2. So the valence band is like a band here, but all the holes are going to be right at the top here. Okay. All right. Now, when I look at this particular one here, when I look at this particular band here, let's say a conduction band here. As I said, in the conduction band, I have a lot of energy states. It's not that this is continuous. I have a lot of energy states here. So between EC1 and EC2, I have huge number of states. And how many states? Well, roughly of the order of number of atoms per unit volume. So 10 to the power 22 states, let's say, between EC1 and EC2. Now, what would be the gap between two energy states? Roughly, if I look at an energy diagram, let's say I go back here to the case of silicon, right? If I look at the extent, if you see the energies here, if I go from here to here, what kind of energy do I see? This is probably somewhere 3, and this is 2. So what is the whole extent of the band? Roughly about an EV, right? So the number that you should carry is 1 EV, 1.5 or 2 EVs is that sort here. So imagine between EC1 and EC2, the energy is about 1 EV, right? And how many states are there in this particular energy level? 10 to the power 22. So what's the separation between two states on an average? Extremely small, right? Extremely small. The levels are very, very close to each other, right? So you can almost think of, even though we know that there are discrete states, you can almost think of it as a continuous distribution, right? And therefore, we have this concept of density of states. When you think of a continuous distribution, so you have a concept of density of states, which tells us how many states are there per unit volume per energy. Okay, so that's the idea is that if I take in this gap here some energy increment dE, there would be a certain number of states in that particular increment, and how many states will be there? Density multiplied by dE. So it will tell us in that small energy increment how many states are there. All right, and now it's not uniform. These states are not uniformly distributed. Okay, so that's why we are using a function. The density of states is a function. It depends. It has a certain profile here. For example, for a 3D silicon, we can approximate density of states like this here. Density is actually goes as square root E. This very small density, the density increases as you go towards higher and higher energy here. Of course, this expression is not valid over the entire band. It's only valid close to the conduction band here. Okay. So the point is that I have lots of states in the conduction band, and the states are so closely spaced that we find the concept of density of states useful. And GE/dE tells you how many states are there within a certain energy increment. Okay. And depending on the nature of the semiconductor, for example, a 3D semiconductor, three-dimensional semiconductor such as silicon, one can show that density of state increases as square root E close to the conduction band. Similarly, if I took a 2D semiconductor, 2D means it's a sheet, right? And it's a sheet of semiconductor. There one can show that the density of states is a constant. If I could make a wire means 1D semiconductor, then one can show that the density of states goes as 1 over square root E. Okay, so I'll not go into the details, but just pointing out to you that density of states, the concept of density of states, that is a function of E, its nature depends on the EK relationship, and also depends on the nature of the semiconductor, whether it's a 3D volume semiconductor or a sheet of semiconductor, or maybe a wire, simple wire, one-dimensional wire. So in that case, the density of states goes as 1 over root E. All right. Again, if you would recall, in all these expressions that you see for density of states, I have put some mass, and I've also added MEDS, density of states mass. So here also a concept of effective mass is used, but then this is an effective mass which is used for density of state calculation. So people have an effective mass which is used for conductivity calculation, an effective mass which is used for density of state calculation. Because remember, if the concept of effective mass is basically you're approximating the EK diagram, right? So it depends on for what approximation, for what which place are you approximating the EK diagram. Okay, if you're doing it for density of states, a different effective mass is there. If you're doing it for conductivity, a different mass is there. Okay, so let's now go forward with this concept of density of states and talk about now how we can use it to calculate the electrons here. Okay. So this is the density of states then that we have here in a typical 3D semiconductor like silicon here. Look at the diagram here. Density of states in the conduction band, it goes as square root E minus EC. The diagram has energy along the y-axis and density of states GE along the x-axis. This EC refers to the bottom of the conduction band. And then you can see density of state increases as square root E minus EC. So it increases like this here. That's how density of state increases. Similarly, for the valence band, the density of state increases like this here. Okay, that's the nature of a typical nature that people assume for 3D semiconductors here. Okay, and of course it doesn't just keep on going like this. As I go further and further, the nature changes. As I said, this is true only close to the conduction band, and this is sort of true only close to the valence band. But it doesn't matter for us because we said the electrons stay very close to the bottom, the holes stay very close to the top of the valence band. So it doesn't matter much how it changes later on. Okay, what its nature is. So now that we know density of states, we want to calculate what is the how many electrons are there in the conduction band, because those are the free electrons that can contribute to current. And similarly, we want to know how many holes are there in the valence band. Okay, N and P here. So then we go to the next concept, which comes from statistical thermodynamics, which says the following, that probability of occupation of a particular energy state is governed by what is called Fermi-Dirac probability distribution function. So it tells us that if you take any state E in equilibrium, the probability of occupation of that particular state is 1 by 1 plus exponent E minus EF by KT. System has to be in thermal equilibrium, and it tells us the probability of occupation. Some of you beforehand, you must have seen when you did kinetic theory of gases, the probability distribution function was Maxwell-Boltzmann distribution function, right? So similarly here, the electrons are, I'll not they're fermions, they obey certain statistics, and the statistics for this is this Fermi-Dirac. So I'm just going to state this particular one. One can do some simple derivations and show where this comes from, how it comes about from, this particular function comes about. But the point to remember, important point is that it's telling us what is the probability of occupation of energy, any energy state E. And it says you know that if you know if a parameter called EF, which is the Fermi level. If you know EF, then any state E that you take in your system, you know what is the probability of occupation. But the big question is, what is EF? All right, where is EF? All right, so we'll see how to calculate that. So now imagine, let's focus our attention on this one here, conduction band. Let's focus our attention on conduction band. The number of electrons, let's say, number of electrons. See, GEDE gives you what? The total number of energy states in an energy increment DE, right? That's the definition of GE. Number of energy states in an energy increment DE. What is the probability of occupation of those energy given by Fe? So what does this product give me? Total number of electrons that exist in energy at energy E, right? The total number of states multiplied by probability of occupation of that particular state. So it gives us the number of electrons that exist at a particular energy E. Total number of electrons in the conduction band will be what now? I simply integrate from bottom of EC up to the top of EC here, right? The top of EC here. So I integrate this DNE from the bottom of conduction band EC to the top of the conduction band. And in fact, I should have put here EC1 and EC2 here. But what will happen is you will see that Fe is such a sharply decreasing function. You know, you can see here an exponential, that the upper limit doesn't really matter. Whether you put EC2 or you put infinity or whatever, it doesn't matter. Okay. So strictly speaking, one should put here EC and whatever is the top of the conduction band, EC2 here. So this tells us that how to calculate the number of electrons in the conduction band. Take density of states multiplied by Fermi-Dirac distribution function, integrated over the entire band here from EC to infinity. And that tells you how many electrons are there. Note how many electrons are there at equilibrium, because the concept of this function is only there at equilibrium. Okay. All right. So since this Fermi-Dirac distribution function is important, let me just illustrate to you a few things about this particular function here. The first thing is, note that FEF is equal to 0.5. Just substitute here E equal to EF, and you get the probability equal to 0.5. So another definition of Fermi energy is what? Is the energy at which probability of occupation is half. Okay, all right. Look at, if I plot this out, look at how this function goes here. So I plotted it versus E minus EF by KT. And this is how the nature of the function goes here. Okay, which is what you see. Now, suppose I take this particular function and I plot it on a log scale, right? Log scale here. So this is log. Look at how it looks on a log scale. What does this show? Tell us that as I go, if I look at this region here, right, all this region here, for energies larger than EF by a certain amount, on a log scale, if it looks like a straight line, what does it mean? It's an exponential. So what you can do is this FE can be approximated simply by exponent minus E minus EF by KT. Okay, that's a very good approximation. You can see here, as long as you are something like 2 or 3 KTs above your EF. So for all energies 2 or 3 KTs above EF, you can approximate it by a exponential here. FE becomes exponent minus E minus EF by KT. Okay. Other things you can, if you want to know, my Fermi-Dirac function is varying, right? It starts from 1 and then eventually goes to 0. What is the, this range over which variation takes place here? So suppose I take 90% probability and I take 10% probability here. This range is 4.4. So it's about 4.4 KT where my 4.4 times KT where my Fermi-Dirac function is going approximately from close to 1 to close to 0 here. 4.4 KT. Okay. So now you can imagine, suppose I start going to lower and lower temperature. What happens to the function? It becomes, this transition region is 4.4 KT. So as T starts going towards 0, this function becomes abrupt here. So when I go to T to 0 here, my Fermi-Dirac function becomes like this here. Okay. Which means all states below EF are occupied. Their probability of occupation is 1. And all states above EF they're unoccupied. Right? So so another definition of Fermi energy, then from this point of view, you can say it represents the highest occupied energy level, especially if I go to T equal to 0. So what is Fermi energy? Is the highest occupied energy level in my system. Because above that, I have all unoccupied. Below that, I have all occupied here. So EF is the place, it represents the boundary here. Now, the reason why I've drawn this particular picture is, although I know Fermi-Dirac function looks like this here, many times for simple calculation, we approximate it like this here. If I want to do a very quick analysis of something and I want to find out, what I do is I think of my Fermi-Dirac function like this here. That below EF, everything is occupied, above EF, everything is empty. Right? So it's a very simple function and I can use it to quickly estimate my electron density, hole density and things like that. Of course, there'll be a little bit of error here because I know there's a transition region. But for a quick estimate, it will give you the order of magnitude and all of that, which is correct. Okay, precise value, of course, then you'll have to take the full Fermi-Dirac function. So that's a very useful approximation. Below EF, all states are filled. Above EF, all states are empty. Okay, let's take an example now. So a hypothetical example of a system where my energy bands are like this. Okay, understand what this diagram is representing now. Y-axis is E, X-axis is density of states. So it shows me two bands, a conduction band like this here, a valence band like this here, right? And what does it show? Density of states is constant. So some hypothetical semiconductor, density of states is constant throughout. And what is the bandwidth? 1 eV here, bandwidth 1 eV here, there's symmetry. And energy gap is also 1 eV, just for simplicity. Okay. What is the density of states? 5 times 10 to the power 22. Note the units per centimeter cube per eV. So density of states are per unit volume and per eV. Okay. So that's the density of states here. Same density of states here. right? So that's a semiconductor given to you, with this energy band structure, which is over here. What we want to know is how many electrons and holes are there at equilibrium in this semiconductor, at equilibrium. Okay, and we would like to know where is the Fermi energy here. Is the Fermi energy here? Is the Fermi energy in the middle of the gap? Is the Fermi energy in the valence band? Where is it? Okay, we would like to locate the Fermi energy. Okay, so first important question is how many electrons and holes are there at equilibrium? That's the simplest problem that I can think of. Now, how do I do that? This is the Fermi-Dirac function here. So again, remember what it was? Number of electrons at any energy is the density of states, dE, multiplied by the Fermi-Dirac function. Okay, so let's focus on this energy increment is dE here. And in this energy increment, I have this many states here, right? Multiplied by the probability of occupation. All right. So total number of electrons in my conduction band will be this one integrated from EC, the bottom, to EC plus 1. This is the entire one. GCE, density of states, multiplied by FED, right? So that's how you calculate the number of electrons. Fortunately, in this case, GC is a constant for us. So we take GCE out. So we write N0 equal to 5 times 10 to the power 22. EC to EC plus 1, simply integrate the Fermi-Dirac function. All right, so it's still a little bit of a problem here. One can integrate. It's not an issue. 1 by 1 plus e to the power x is not an issue to integrate. One can do that here. But there's no need to do that because what kind of an electron density would you expect in a semiconductor? Much, much smaller than this particular value here. Okay, typically. Okay, so if that is the case, note that if my electron density in my conduction band is, let's say, a typical number to keep in mind is 10 to the power 17. So if this is 10 to the power 17, and on the right hand side I have 5 times 10 power 22, what can you guess about Fe? Fe must be very, very small, right? Very, very small means what? This exponent E minus EF by KT must be very, very large, and therefore I can neglect 1. And I can approximate my Fermi-Dirac function as exponent minus E minus EF by KT. All right, so that's what we are going to do. We'll substitute here. Now it's a simple exponential, straightforward integral, and I get N0 here, this approximation we are making, and we get N0 equal. All right, okay. Now, so we are doing EC by EC plus 1 exponent minus E minus EF by KT, right? That's the integral. Now, you can see that this function is dropping so rapidly that EC plus 1, I can, for all practical purposes, take it as infinity. Doesn't matter at all. Okay, so we do that, and then, so EC to infinity, we do integrate, and we get N0 equal to 5 times 10 to the power 22 into KT exponent minus EC minus EF by KT. So we get this expression here. Okay, KT, of course, I know, 26 milli electron volt. So we put in there 26 milli electron volt at room temperature. So I get N0 equal to 1.3 10 to the power 21 exponent minus EC minus EF by KT. Where is my EF going to be? Well, I don't know because I don't know N0, right? Both N0 and EF are going to relate it together. But where is the guess? Because N0, as I said, a typical value may be 10 power 17 or 16 or 14. Note that this is much smaller than 10 power 21. So EF is going to be somewhere below EC, right? Somewhere below EC. I don't know where it is, but it has to be below EC here. Only then will I be able to satisfy him. So N0 is 1.3 into 10 power 21 exponent minus EC minus EF by KT. Say N0 is 10 power 12. I'm just guessing. What will it tell us? We can immediately then calculate EF. EC minus EF by KT turns out to be minus 21. And EC minus EF turns out to be minus 0.54 EV. So it's, 0.54 EV below my conduction band here. Now, was my approximation correct that I approximated Fermi-Dirac by exponent? You can see here EC minus EF by KT is 21. EC minus EF by KT is 21. So anything above will be even larger. And therefore, if you go back and look at this exponential here, e to the power 21, right? So that's huge. So obviously, 1 you can forget about it. Okay. So EC minus EF then is minus 0.54, and we know. So if you know where N0 is, how much N0 is, you know where the Fermi energy is. On the other hand, if you know where the Fermi energy is, you can calculate where N0 is. Okay, both of them are related together. All right. So that's it. So this is the picture that we have then. We have N0. How much time do we have? All right. Bell is gone, is it? No? N0 is 1.3 into 10 power 21 exponent minus EC minus EF by KT here. So that's the picture that we are building here. I have EC, bottom of the conduction band. I have EV, bottom of the valence band. And somewhere in the somewhere below EC, I have EF here. Well, you may still be wondering, well, if below, and we calculated that for a typical value, let's say 10 power 12 or 10 power 13, it came out to be 0.5 or so here. So it's appearing to be somewhere in the middle of the energy gap here, EF. Okay. What about the definition of Fermi energy? That is the Fermi energy is the place where probability of occupation is 0.5 and is in the forbidden gap. Does it conflict? Fermi energy, by definition, is the place where probability of occupation is 0.5, and this is the forbidden gap. Is there a contradiction? It's only saying probability of occupation. Forbidden gap means what? I have no states there, and therefore I have no electrons there, right? So there is no, don't get by that. All that is saying is, if there were an energy state, its probability of occupation would have been 0.5 here. And we could get, as I said, if you introduce some defects, you could get some states in the energy gap. And then we can calculate how much probability of occupation of that particular state is. Okay. All right. So let's stop here. We'll continue from this point onwards and look at electrons and holes.